Okay, so I will started the recording. So we'll be covering clogged CMOS SR latch using AOI gates. All right. So let us draw the gate level circuit of clogged CMOS SR latch. So how does the gate level circuit looks like? Anyone remembers? AOI means AND or invert. Okay. So how to start? Anyone? What do we have first? AND gate, right? So draw two AND gates, and then the output of the AND gate will go to one of the inputs to the NOR gate. Okay, like this. Okay, this is Q bar, this is Q, and one of the output will go over here. Now tell me, where will you connect S, R and clock? So the common terminal here will be clock, this will be S, this will be R, and that's it. Any cross couple thing, here it is. So this is my clocked SR latch using AOI gates. Okay, these are all active high. So that means when the clock is 1, then my circuitry of SR latch is active. Then my input SNR influence the output. Alright? Yes, Ron. Now let's draw the truth table. Don't wait for me to complete. Do it along with me because there are some topics to go. So let's draw the truth table. Okay, tell me if these are the inputs and this is my outputs, and we'll write the operation. So if input, this is clock is one of the inputs, S and R. Output is Qn plus 1, Qn plus 1 bar. I hope it is visible. Okay, so when the clock is 1, then we have active phase, right? When the clock is 0, it doesn't matter whatever S and R is, the output will be the previous state. Okay, so this is hold operation. Okay, so tell me, whenever S and R is 0 0, what do we have over here? It will hold the previous state. Okay, so this is hold again. Then when S is 0, R is 1, what will be my output? 0, because reset is 1. Correct? So what is that operation called as?
Reset.
Yeah, reset. Correct. When set is 1, reset is 0, output will be 1 and this will be 0. This operation is set. Then if both are 1 1, then what happens? Output will tend to 0. So it is what is the state called as?
Not allowed.
Yes, invalid or not allowed? We write invalid or not allowed. Alright, so please note down the truth table. With the help of this, we will build the gates. We will verify whether the functionality is correct or no. So in the exam also, you can draw this gate level logic, but this doesn't carry any marks. This will help you out, to write the equations of Q bar and Q. That's it. So let's implement this clogged SR latch using static CMOS logic. So we will be using static CMOS logic. Have you noted down the table, truth table?
Just a second.
So this schematic is called as gate level schematic, which you have studied in your lower semesters in digital circuits. You have drawn all gate level circuits, right? But now we will be drawing transistor level. So we will be implementing clogged CMOS SR latch using static CMOS logic. Can we start now?
Yes, sir.
Okay. Now tell me, if this is S and this is clock, what will be this over here?
S dot.
Yes, correct. Similarly, this will be r dot clock. Now tell me if this is q bar and if this is q. What is q bar equal to? This is a NOR gate, right? So q bar will be equal to
Complement addition of the whole.
q plus clock into s, right?
Yes,
The whole bar.
yes, sir.
And what will be q? Q bar plus r dot clock, the whole bar. So please write these equations, the whole bar. Okay, so what are the two equations? We'll write it down again. Q bar is q plus clock into s, the whole bar, and q is q bar plus r dot clock, the whole bar. Alright, so we have to build this using static CMOS logic. And static CMOS logic, we know we have a pull up and pull down. So let's draw this logic now based on these two equations. Now, first we will implement Q bar logic and then Q. So what do we have in the pull down? Pull down we have a NMOS transistor in parallel to two NMOS transistors in series, right? Yes or no?
Yes, sir.
So let me draw this. This is S, then this is clock, and in parallel we have Q. This is Q, like this. Pull up network, what will happen? Pull up network will be exactly reverse, right? So there SN clock will be in parallel or series? SN clock, transistors with the input SN clock.
Parallel.
Yeah, this will be in parallel and this will be in parallel to clock. And then in series, what do we have? This is S and clock. In series, we will have a PMOS transistor with the input Q, right?
Yes, sir.
And where will be my output going? Output is Q bar, right? This one. This is Q bar. So please join Q and Q together because we have common one. These are this are together. So this is Q, this is Q bar. Red one is Q. So and one more thing is missing. This will be VDD. Yeah. So my circuit for Q bar is complete. This is complete. Now we go for Q. So for Q similarly we have Q bar plus R clock. So please draw this in your books. Yeah, I guess you have understood the pattern now. Please complete the design. So here we will have a Q bar. So Q bar deliberately I am drawing it over here so that I can join them and connect them together. And here will have I have R and clock. Okay. And in a pull-up network, R and clock will be in parallel. PMOS transistors with the input R and clock. And then Q bar will be in series with the input Q bar. Alright. So this is R clock. So let me draw Q bar now. Q bar will join with blue color and it's joined over here. Alright. This is Q bar. And where will be Q? Q will be connected over here. This is output is Q, right? So this output will be Q. Okay, so this is the design. So the transistor count is we require 12 transistors to implement this logic. 6 over here and 6 over here, so total 12. AOI base circuit, what is the advantage? Do you know? And or invert, what is the advantage? Advantage is that the transistor count is less. As you can see here, we require 12 transistors. If we follow the traditional method, it will require more than 12. So that is the advantage. Alright, can we check the working once? You have drawn the circuit? Everyone?
Yes, sir.
Yes, sir.
Okay, now let us check one of the conditions. Let me take light green color or this pink color. Okay, so let me say, what should I condition? I will check set condition first. So clock is 1. Okay, clock is 1, then S is 1, S is 1, and then clock is 1, S is 1, R is 0. So R is 0. So tell me, this upper one will be off because these are PMOS. This will be on. So what will happen to Q? What will happen to Q bar? Sorry. Anyone?
It will get pulled down.
So it will be 0, right? Q
Yes,
bar
sir.
will be 0. So this will be 0. So this will be 0. So this will be NMOS pull down will be off. It will be on. So Q will be 1, right? This will be 1. Correct? And is the correct output? Q is 1, Q bar is 0. So it's giving us the set condition. Is this correct? Did you check it out?
Yes, sir. It's
Okay. Now we'll check the other condition. Let's check the hold condition now. So now clock is 1. Okay. S is 0. R is also 0. So this all will be 0. Clock is 1. This is 0. This is 0. Clock is 1. Now tell me. For this to happen, it is holding the previous state, right?
Yes, sir.
So what is the previous state? Q is 1. So if we let Q equal to 1, then Q bar will be 0, right?
Yes, sir.
So this will be 0. This will be 0. This will be 0. So now output is correct or no? Check. Q is 1. Q is 1 is going over here. So it's the previous state only. Yeah, correct it is. Q bar is 0 is satisfying this condition. Yeah. Alright. So in this way, you can check under other conditions also to build this circuit. Alright. Now let us check one more condition, that when the clock becomes 0. When the clock becomes 0. Now this is 0, this is 0, clock is 0. Now the clock is 0 irrespective of S and R. It will hold the previous state. So let's say S is 1. What was the previous state? Irrespective of S and R, right? Let S and R be 1 and 1. So let's say it is 1 and 1. Does it matter? Now tell me, what should be Q and what should be Q bar? Can this yeah, tell me.
So the Q should be 1 since the clock, the PMOS is on, but SPMOS is off.
So if Q is 1, Q bar will be 0, right?
Yes, sir.
Yeah. So it's holding the previous state only, as you can see, right? Previous state was Q was 1, Q bar was 0, right?
Yes, sir.
So it's the hold condition. So clock should be active basically. Alright. So when the clock is active, only then this clocked SR flip flop will work.
Right, sir.
Okay. So let's go to the next one. I hope everyone has completed this.
Yes, sir.
Next one, can I leave this clocked SR latch using OAI gates up to you to complete? I'll draw the gate level schematic and the truth table. Static CMOS logic, can you do on your own?
Yes, sir.
So let me write. So please write this second one. Clogged SR latch using OAI gates. meaning or and invert. So or will be like this using or gate, then we have and gate, and then we invert it like this. Understood? So here one of the input is clock, other one is SNR, and your output is Q. Here it is Q bar, and here you connect a cross couple connection. Yeah. So that's the gate level schematic. Note over here S, R and clock are active low inputs. What do you mean by active low? Means they are active when it is 0. Are you understanding? So here if I draw the truth table, inputs, outputs and the state, help me out in this. Clock has to be 0 or 1. Absolutely correct. S, R, Qn plus 1, Qn plus 1 bar. I hope you know why I write Qn plus 1, because it will hold the previous state is Qn. So this will be x and x, this will be 0 0 0 1 1 0 1 1. So here it will hold the previous state. So this is hold state. Here tell me 0 0 is hold state or 1 1 is hold state? You remember we have done this before in one numerical. So here 1 1 is hold state. It will hold the previous values. And 0 0 is not allowed. Okay, because it will give you the output 1 1. When S is 0, it will give output as 1. And when R is 0, it will give the output as 0. So this is set and this is reset. Alright. So now I hope you have completed the table. What is the output of this OR gate? What do we write over here?
S plus clock.
S plus clock. Here we write R plus clock. Here what do we write? Q. This is Q bar and this is Q.
S plus clock dot Q the whole bar.
Okay, yeah, correct. S plus clock dot Q bar, right? The whole bar.
Yes, sir.
This is R plus clock dot Q the whole bar. So please write down this equations. It's only about equations. With the help of equations you can implement it very easily. This is S plus clock dot Q bar, and Q bar is R plus clock into Q the whole bar. Okay, now I'll give you all 3 minutes, 3-4 minutes. You implement this design using static CMOS logic. Okay, please complete it. I'll come back in 3 minutes time. Alright, so keep this ready. Let's verify the design then. Yeah, so sorry for the delay. So let's continue with the design. You all have completed it? Yeah, students?
Yes, sir.
Okay, let's verify the design quickly. So here we have s plus clock dot q bar. So we'll implement the first logic. So here NMOS network will be two NMOS transistors in parallel with input S and clock will be in series with Q bar. So let's draw. Let me adjust my screen. Yeah, let's complete it. So here we'll have two of it. This will be Q bar, and these two transistors will be with input S and clock. This will go to the ground. And at the PMOS side, what do we have? S and clock will be in series. Correct? Is that what you got?
Yes, sir.
S clock, and that will be in parallel with uh, Q bar. Alright, so this is my network, and here is my output. This will be Q. Let me mark that as red. So this is Q, and you can draw the same colors, but see to it that there is no overlapping. This is Q bar. Alright, now let us quickly draw the next one on the similar lines. So here we have, oh sorry, orientation wise I have to put it like this. This will be Q, and then two NMOS transistors will be in parallel with the input R and clock. This is clock, this is R. And on the PMOS side, the two ones will be in series. So please check your design if this is correct. And then one PMOS transistor will be again in parallel with them. So this is VDD, this is Q. Yeah. Your output will be, I think, Q bar, right? This is Q bar. So this will directly go over here. And did you please check your designs if this is correct? Same thing you have drawn?
Yes, sir.
Okay. And do not forget to mark this dot. Dot means there is a connection. Alright. And again the transistor count will be 12. Okay. So now we have completed clocked SR latch. The next topic will be JK flip-flop. Ready everyone? Now I will be slightly increasing the pace. Hello.
Yes, sir.
Now there is one more category of clocked NAND base. I'll show you without IOI gates. So they can even ask you draw or implement clocked NAND base SR latch. So what is clocked NAND base SR latch? You use NAND gates only. So here we have like this, two NAND gates connected over here like this, and here one input will be common clock, other input will be S, R, and output will be cross coupled like this. So it doesn't follow AY gates. This will be Q, this will be Q bar. So you know what is the disadvantage of clock NAND based SR latch? The number of transistors required will be more. Okay, so you require active high inputs. So please implement this design on your own. Active high inputs. So AOI gates and OAI gates can be implemented using lesser number of transistors, but using NAND based clocked NAND based SR latch and clocked NOR based SR latch will require more number of transistors. So can you do this on your own implementation? Okay.
Yes.
Okay. Now let us go to clocked JK latch. I'm still calling it a latch. Okay. So write down third one for the day, clocked JK latch. So you tell me what problem it is solving JK latch. This is NOR based. Tell me.
Sir, the not allowed condition in case of SR is solved by using truth table.
Solved completely.
Not completely.
So this becomes toggle, na? Remember?
Yes.
It keeps on toggling between 1 and 0, right? It
Yes.
is, and what it is called as? Remember, there is a technical name for it. Race around condition. Have you heard?
Yes.
So that problem of not allowed is solved, but partly solved. Now let's see how it is. So first draw the circuit, gate level implementation. So it is AOI. First AND gate will come, then will come the OR gate, and then we connect a NOT. So it becomes NOR. So now this is a level up in design. Okay, here we have J and K as clock. Anyone remembers how do we connect it completely? This is J, this is, let's say, K, this is J, and here it is Q bar. Anyone remembers it? Is this complete or still we have something left? Is this proper? Tell me. No, we have three inputs. So one input from here is going to the output directly. Remember? JK flip flop.
Yes.
This is the circuit. So if you remember the gate level circuit, then only you can write Q and Q bar equations. So remember, the advantage of using AOI gate, logic implementation is it uses less number of transistors. So please draw the diagram. Now we have to carefully write the logic. Next we write the truth table. So clock J, K, Qn, Qn bar, and the operation. So this is 0 irrespective of the inputs. Output will be holding the previous state. Then 1 1 1 1 0 0 0 1 1 0 1 1. This 0 0 is again holding the previous state. 0 1 will be, output will be 0, Q bar will be 1, and this is reset. Now when J is 1 it will be set, and when J and K is 1 1, that was not allowed condition, right? But here it will be Qn bar Qn. This is called as toggle state. So this technique or this state is also called as a race around condition. There is a race between a 0 and a 1. Race around condition. Okay, so the active phase of the clock, this is my active phase of the clock. So whenever the inputs J and K are logic 1 of the circuit, output will toggle continuously until clock becomes inactive or goes to 0, or one of the input signal goes to 0. Okay, so it will keep on toggling between 1 and 0 until your clock becomes inactive, that is clock becomes 0 or one of the input goes to 0. Okay, to help me out in writing the equation now, what will be this? Come on. AND gate, na, 3 input AND gate.
Q dot K dot clock.
This is Q, this is Q bar, so it will be Q dot K dot clock. Perfect. This will be uh, Q bar. This will be Q bar dot J dot clock. Now tell me Q. What will be this? Here it is Q bar, here it is Q. Yeah, this is tricky. Tell me. Yeah.
Q dot K dot clock plus Q bar the whole bar for Q.
Yes. Q dot K dot clock plus Q bar the whole bar. Absolutely correct. Q bar will be similarly q bar dot j dot clock plus q, the whole bar. Is this correct? Q bar is
Yes, sir.
correct? Okay, please write it down separately. So q is q dot k dot clock plus q bar, the whole bar, and q bar is q bar dot j dot clock plus q, the whole bar. So we have to implement this using static CMOS logic. I told you it's slightly level up. Static CMOS logic. Everyone ready? You have written up till here. Please complete it up till here. Okay. Can we start with the design, everyone?
Yes, sir.
Okay. So here we'll using static CMOS logic. So in static CMOS, the lower one will be uncomplemented form. So NMOS transistors, three NMOS transistors will be in series with parallel with one NMOS transistor. So let us draw the NMOS network. So we have over here, first we'll implement Q bar and then we'll implement Q. Okay. So here it is. You can anyway go other order also, but that is fine. I'm starting with input as K, J. So this is three transistors in series with the inputs J, clock, and this will be Q bar, and one more transistor will be in parallel with them with the input Q. So this is my NMOS network for Q bar. Then PMOS network will be these three inputs. There will be three transistors, PMOS transistors in parallel, right? Here it is 1, 2, and 3. And what are the inputs? J, clock, Q bar. So all of them will go to VDD. Okay. Now what they will be seen in series with? They will be series with PMOS transistor with the input. What input? Yeah, Q. So this is Q. So your output will be Q bar. Correct? And this is my Q. So please complete this. And then similarly I'll draw the other one. Other one is for Q dot K dot clock. So same design, same pattern you repeated, only the inputs will change. Three transistors in series, that is in parallel with another transistor, and then in the pull up network again three transistors in parallel, and all of them are in series with another PMOS transistor. Yeah. Now this is K clock. Let me write it here first. K Q clock, right? And here it will be Q bar. Oh, I should have drawn it here. Okay, no problem. Q bar I will don't change it in your case. I should have drawn this over here so that this will join them together. It's okay. So this is J, no, not J, Q, K, and clock, right? And this is what? Q, right? Q. This also Q. Q bar or Q?
That will be Q bar.
Yeah, here it is. I'm checking here. Okay, yeah, this is will be Q bar. This also will be Q bar. This will be Q, K, clock. Now let's join them together. This is Q bar. These two are also Q bar. So connected together. And what about Q? Q will be the output, right? So this is Q and this is also, yeah. Please complete the design. How many transistors it required? 16. If you do a NOR or NAND based design, it will require much more transistors. Alright, can we check it's working first? Everyone?
Yes, sir.
Okay, let us check two states. So let us check first state as clock as 1. Which color I should use? One bright color. Yeah, this clock is 1. So everywhere there is 1. Clock is 1. Okay, and J and K we reset condition. So J is 0, K is 1. J is 0, K is 1. Now tell me, what should be QL Q bar? Hello? J is 0, K is 1 and clock is 1.
It should hold the previous state, right? Toggle condition.
No, why? K is J is 0, K is 1 na, no toggle. Toggle happens when J and K both are 1.
Oh, my bad.
So basically this part is off, it cannot go down because this is 0. So if Q is 0, then also again this will be cut off, then Q bar will be 1 basically. So right now if Q is if Q is 0 if Q is 0, NMOS network will be off but PMOS network will be on, right? Hello, that is
Yes,
logical,
sir.
that is logical solution, right? And if Q bar if Q is 1, if Q is 1, this will be on. Both the cases are there. So which one we will put? Let's assume one and go ahead. Okay,
Yes.
let's say this Q is 0. So Q is 0 means this will be on and J is 0. So it output will be, Q bar will be 1. Correct now? So Q bar is
Right.
1, it will go over here, this becomes 0, this becomes 0, Q bar becomes 1. Is this condition satisfied? Then Q will become 0 if Q bar is 0. And if Q bar is 1, then Q will become 0, right?
Yes, sir.
Okay, so this condition is getting satisfied. Now let us change the inputs. Let us say J and K. J become 1 now. J becomes 1. Now tell me what will happen. In the next cycle, J has become 1. We don't know about Q and Q bar. Previous state was 0 and 1. Now what will happen?
So now Q will become 1
Why?
because it will reach toggle state because J and K both are 1.
So what will Q become? Q and bar, right? So this will become 1 and this will become 0, right?
Yes, sir.
So this is 0, this is 0, Q is 1, Q bar becomes 0. So there is a change of state. This Q becomes from 0 to 1. Yeah. So there is a change of state from 0 to 1, right?
Right.
For Q, and for Q bar it is from 1 to 0. Now unless you change any one of the inputs, it will remain in the state, correct?
Yes, sir.
Now let me change the state to let me make J as 1 and K as 0. So K is 0, here K becomes 0. Now what will happen? Now let's see what will happen. What should be the output? J is 1, so the output Q will be 1, right?
Yes, sir.
Is Q 1 only? Yeah, Q is 1 only, no?
Yeah, Q is
So
1.
it's not changing the state, right? Unless we change the significant state. It's toggling between 1 and 0 only. If we
That's
deactivate if we deactivate the clock, then there will be a change in the state. So unless that happens, it will remain in the toggling condition 101010. Okay, so that's the working. Any doubts over here?
no, sir.
All right, so let us implement the next one. Write down, I think this is the fourth one for today. Yeah, so we will be implementing. So this was using AOI gates. All right, now we'll use clock JK latch using NAND gate based clogged JK latch, NAND based. So what do you mean by NAND based? Both the gates are NAND gates. So quickly draw the gate level. This will be J, this is K, common clock. One of the inputs goes to this output. This is Q, Q bar, and cross coupled output. Okay, and this third input is going over here. All right, complete this. Truth table will be it will be active high or active low. You can keep it as active high also, no problem. So truth table will be same as the previous truth table which we have drawn over here. This truth table will be same. Now tell me the equation over here and here. Output of first NAND gate, what it will be? Hello, help me out in writing this.
Sir, it's clock dot J dot Q the whole bar for the first one.
Okay, yeah, correct.
And for the second one is clock dot K dot Q bar the whole bar.
Yeah, correct. So please complete this. Yeah, clock dot J dot Q bar, the whole bar. Here it will be clock dot K dot Q, the whole bar. So here Q will be same thing multiplied by Q bar, the whole bar, right?
Sir,
Yeah,
in the above one it should be Q, right? Because the input is coming Q, not Q bar.
here na.
Yeah,
Yeah, inside it should be Q, outside it will be Q bar, right?
yes,
So K dot clock dot
Q bar.
Q bar. No. Wait. There is some problem. Wait. This design slightly AOI gates is slightly different there. This third terminal, I don't know whether if you remember it or no. In last design it was correct, but here this one goes to Q bar. That is how it is built. And this third terminal doesn't go over here, it goes to Q. ऐसे था ये design. Now it is okay. Now will it be Q bar, right?
So this type of design is specific for which base gates?
Which only for JK flip flop.
Okay.
For AOI gates we have done now the plainly here. See, here there was no complexity. And only thing was use and, or, and invert. That's it. But in this case, you will require this one. I mean, you have studied in your digital design, right? Why the gate they are connected this manner. Now we are just drawing the transistor level implementation of the same. Now write the
Yes.
equations. Q is J dot clock. Now it will come Q bar, right?
Right.
That's what I was wondering, why it is coming Q. So this will be Q bar dot, what it will be? Q bar,
Super.
the whole bar. That's why I'm writing this bar like this. So this also will be bar, or else a lot of confusion will be there. This will be K clock dot Q bar dot Q, the whole bar.
Right.
Yeah. The truth table will be same. I'm not drawing it. We are interested in implementing. So we'll open it by De Morgan's theorem. The first part we can split it up using De Morgan's. How we can write a dot b dot c the whole bar. How we can write it using De Morgan's? Can we write it as a plus b plus c, a bar plus b bar plus c bar? You can write it like this.
Yes.
The whole bar will come. No, the bar is there. So here it will be, yeah, j dot clock dot q bar, the whole bar into q bar, and that also whole bar. How we can open it up? Anyone? Internally whatever we have written, it will become j bar, right?
Yes.
Plus clock bar plus q. Do you agree this? Dot q bar, the whole bar. Do you understand? It's a bar, right? So I've written j bar, clock bar, and clock bar ki jagah I've written q because it is c bar. So next will be, this is tricky, huh? Q bar, what it will be, k dot clock dot q bar dot q the whole bar. This can be written as k bar plus clock bar plus q bar into q the whole bar. Please check if these equations are correct.
Yes.
Now we have to implement this using static CMOS logic. So I hope you have understood how to write this equation from gate level schematic. Gate level schematic itself carries doesn't any marks, but it's helpful for writing the equation for output Q and Q bar. Now it's pretty simple. We have to implement this using static CMOS logic. So let's go ahead and start. Okay. Okay, this again is uncomplemented one. It's very simple. Three transistors will be in parallel, which will be in series with another one. So let's start with the NMOS network. So this will be Q bar. We have to very careful about Q, where we write Q and where we write Q bar. So there are three PMOS transistors, NMOS transistors with the input J bar. We are implementing upper one, J bar. Then it will be clock bar, and here it will be Q. This is Q bar. About how it will be, three PMOS transistors will be in series, right? And that will be in parallel with another PMOS transistor with input Q bar. Yeah. So draw three PMOS transistors in series with the input J bar, clock bar, Q bar, and that is in parallel with input Q bar. I think this is Q, no?
Yes, sir. It's Q.
Yeah. Connect them together. Now where is my output? Output is Q, right? This is Q and this is Q bar. This is VDD, and these two Q bars you can tie together later. So this is Q. Now we implement Q bar. So exactly the same thing, only orientation wise I'll keep it different, like this. I know I can connect them together later. So draw three PMOS NMOS transistors in parallel, which is in series with a single NMOS transistor. So here this will be, I think, Q, this will be K bar, clock bar, and Q bar. I hope I'm doing correct. These are three PMOS transistors with input K bar, clock bar, and Q bar. Alright, is this correct? Please check. The output will be Q bar. So Q bar we can tie it together like this. And here this output will go over to here. This Q, actually orientation I've done it wrong. This K, this Q and this Q, they'll join together. Okay, so that is the diagram, static CMOS diagram for this. Do we require here we see 16 transistors, right? Do we require any other transistors? Please implement first. Oh, sorry. Do we require any other transistors? I told you
J bar and K bar.
J bar, K bar, and clock bar, right? So 6 additional transistors.
600. 600.
So earlier examples, why didn't we use this? यहाँ पे क्यों नहीं use किया?
Sir, because there was no J bar and clock.
No, there was not input. Input में bars नहीं था, right? Output में bar is fine, but यहाँ पे here in this case there is a bar in input also. Okay, so here we'll draw 3 CMOS inverters just to represent that. So this is J bar. Okay, then we have another K, this will be K bar, because we are using this in the design, right? And then clock bar. See how I am writing bar as a word. Okay, so total transistor required is 22. The complexity is slightly going on increasing with every design. Alright, everyone completed? Okay, great. Okay, let's consider one example over here. This is tricky to explain, but it's okay, we can explain that. Explanation can you carry out on your own? I mean, you can have the truth table and verify on your own. I'd rather do the other designs then. Is it okay? Hello?
Yes.
Okay, fine. So please, follow the technique which has been taught before for apply the inputs over there temporarily and check whether your output is getting satisfied or no. Now we'll study one more category of JK latch, that is, do you know preset and clear condition in digital ICs? Have you heard of it? So write down clogged NAND based JK latch with active low preset and clear. What is the meaning of preset and clear? Anyone? You have studied this before, no? What is preset and clear? Hello. Preset means, clear means it will clear the output, right? Very preset means it will set the output to one. Yes, no?
Yes.
So we need to implement this using static CMOS logic. First implement it using gate level schematic. So what will be the change? Let's draw it. So like we have two NAND gates followed by another two NAND gates. These is directly connected over here. Then everything is similar. Right at the last step there is a change. This is J, this is K, this output is Q, this is Q bar. Your third input is going to Q bar, your third input is going to Q, yeah, Q, and there is a cross coupled also, right? Like this. Yeah. So where is the preset and clear? This is the same diagram as last time, right? Preset is over here, ये वाला. So we call it as preset bar because they are active low inputs, and clear bar. So please draw this. Completed? Hello.
Yes, sir.
Okay. Now we have to write down the equations, and also before that the truth table also will come. So let's go to the truth table. It's a long truth table, so please implement. First write down the equations. Equations will be easier to write. So what will be over here? Here it will be J, right? J dot clock dot Q bar, right?
Yes.
The whole bar, is it? And here it will be K dot clock dot Q, the whole bar. Acha, what will be Q equal to? This is one input. Second input is preset bar, and the third input is Q bar, right?
Yes, sir.
J dot clock dot Q bar, the whole bar, dot preset bar dot Q bar, the whole bar, and Q bar will be K dot clock dot Q bar dot clear bar dot Q, the whole bar. So these are the equations. Okay, this you can simplify it further as this tree we can write it all as J bar plus clock bar plus Q into preset bar dot Q bar, right? Yes or no?
Yes, sir.
And this also De Morgan's law, K bar plus clock bar plus Q bar into clear bar dot Q, the whole bar. This again also using De Morgan's theorem. So we'll use this expression and this expression to implement this clock based NAR JK with preset and clear conditions, clear pins. Can we now go to the table, everyone?
Just a minute.
Okay.
Just a second.
Okay. I should let you know what is upcoming. Upcoming is master slave JK flip flop. You have heard of it, right? So
Yes.
as you can see, with every design, the number of transistor count is increasing. So don't get intimidated by it. You have to just follow the logic. Now let's write the truth table. It's a big one, so it will require half a page. So here it will be clock J K Qn Qn bar preset bar clear bar Qn plus 1 Qn plus 1 bar and the state. So clock will be 0, this will be, doesn't matter, let's say this is 1 and 1. Preset and clear are inactive, are active basically. Inactive or active? 1 matlab it is inactive, right? So this will be holding the previous state, so this is hold state. Okay, this is clear to you. Next we will go for 1. So if j is clock is 1 and j and k is 0 0, let's say the previous state we doesn't care, this is inactive, so it will still continue to hold this state, previous state. Why? Because 0 0 is there. Then we have gone to 1 1 and here the state is 0 1 0 1. Let's say the previous state is 0 1 and now the next state has become 1 0. So now let's say the previous state, the preset and clear was off, and now clear terminal is turned on by giving it 0. So what will be the output? Will it hold? Yes, it will hold. So this will be hold and this will be reset. Why this is reset and why this is hold? Hold, why this is hold is because preset and clear both are inactive, so it will hold the previous state. Why this is reset? This is reset because we have cleared it, cleared the output to 0. That is why it is 0, not because of hold. Are you understanding what I am saying? Hello?
Yes.
Now see next case, again we have 1 clock as 1, this is 1 0 1 0. Okay, let's say that the previous state is 0 1, next state will be 1 0. So the preset and clear, let's say it is preset is on, so it will set, because of preset have been active, so output will be 1 0. Now let's say the preset becomes inactive, now what it will do, it will hold the previous state, right? So this is set and this is hold. Hope it is clear. Now we'll go to the last state. Last state, the previous state will be 0 1, this will be 1 0, this will be 0 1 1 0. So here what you will get, preset. So preset meaning 1, q is 1 and q bar is 0, and here clear is active, so it will be 0 1. So this will be set reset condition, and that is why we were not getting we were getting a not allowed state, now we are getting a set reset state, right? Understood this table? Yeah, here I marked preset and clear as active only under these conditions. Here also preset is active, so it will bring the output to 1, and here clear is active, it will bring the output to 0. So this is the additional things which we have to take care. Alright, can we move on to the implementation level?
Yes.
Completed the table, right?
Yes, sir.
So here it is, q is j bar plus clock bar plus q dot preset dot q. Let's implement this. Let me rewrite the equations. Q is j bar plus clock bar plus q dot preset bar q bar the whole bar, and q bar is k bar plus clock bar plus q bar into clear bar into q. Alright, so this is by De Morgan's theorem, which we have seen earlier, and let's implement this. Remember that preset and clear are active low. Okay, so let's start building the network static CMOS logic. So here it will be 3 transistors in parallel. Connect them together. My inputs are J bar, clock bar, right? And this will be Q, right? Okay, and this will be connected to preset and Q. They both are in series. This is preset bar and this is Q bar, right? What will be the pull up network? This is pull down network. Pull down network I have drawn a little smaller. Okay, this is not a. Please start implementing the design. This is input, how much? This is preset, right? Bar, and this will be Q bar. Now okay? Hello?
Yes, sir.
Then there will be 3 transistors in parallel with the input J bar, clock bar and Q bar. They will be in series with another PMOS transistor. This will be oh sorry, I did a mistake. There will be 2 transistors right over here. Why? Because we have one input with preset bar and one input with Q bar. Alright, so this Q and this Q
So
bar,
they would be in parallel, preset and Q bar.
what?
PMOS pull-up network. There will be 3 parallel lines, right?
Yes, correct. Because they are in series over here, right? All 3 are in series, so here it will be all 3 will be in parallel. Yeah, yeah, thank you for telling right now. This will be preset bar and this will be Q bar, right?
Yes, sir.
You take a careful look at this design because this is what you will get in your assignments. Very soon I'll be releasing assignments in first week of Feb, so there you can start designing your designs. So this is Q. Okay, you have to be very clear. So now again we'll do the same repeat design. Okay, for a Q bar. So Q is complete, now Q bar. Even one mistake and your design will go wrong. Here we'll have 3 transistors. Again I have drawn in them in series. They will be in parallel, right? So 1, 2 and 3 of them are in series. Same logic. So here we have Q bar, preset bar. Here we will have J bar, clock bar and Q bar. Okay, your output is Q bar.
Or in place of preset bar, there is a clear bar.
Oh, sorry, I think I was writing the other case. You have to write the first case, right? Second wala.
Yes.
This will be clear bar. This will be Q, right? This will be K bar, clock bar, and Q bar. Now it's fine. And this output will be Q bar. Then down, we will have all the three of them in series, and then these three will be in parallel.
Sir, it would be better if you write Q outside, but you have to connect it. It doesn't.
No. Wait. I understand what this Q only matters. Acha, this Q you are saying, na?
Yes, sir.
Yeah.
Forward.
This will interchange. Yeah. Clear bar and Q. Yeah, that's good. This also will write it as Q, right?
Yes, sir.
Q. We can connect. Good idea. This will be K bar, clock bar, and Q bar. Is this okay now? Hello?
Yes, sir.
Okay, this also orientation, I'll change it. This will be Q bar. Now Q bar, I'll connect them together. This is Q bar and this is Q bar, right? Then blue one will be Q. Any mistake, any other mistakes, please check it, because I'm doing it live, so it may tend to do the reading mistake, but this is the design. Sorry for untidiness, but I'm doing it fast, that's why it's coming this way. So how many transistors is required? Anyone counted? This is 5 here, 5 here, 10, 10, 20, right? 20 you can see, but how many more? How many more you require?
6, sir.
6 transistors for J, K and clock, right? So you have clock bar, J bar, K bar. To generate this we require CMOS inverters. So total 26 transistors. As you can see, the number of transistors are increasing. Next upcoming topic is JK flip flop, the master slave JK flip flop. Okay, everyone done with the design?
Yes, sir.
Now you can check this truth table at your own time. Right now if I do it, that will be end of lecture. I have to complete master slave JK flip flop before we leave today. Okay, so do you know this JK flip flop eliminates the not allowed condition state in SR flip flop or SR latch, right? SR is set reset. You know the JK flip flop is named after its inventor, right? Jack Kilby.
Yes, sir.
JK flip flop, which suffers from a timing problem called as race. That means this is the race condition, right? This one is the race condition. Okay, this is called as race condition. That means if the output Q changes the state before the timing pulse clock T has changed, time has to go to 0. I will tell you why it is possible. You need to keep the time period very small. I will show you an example how it has happened. Okay, so this race condition can be avoided in master slave JK flip flop, because what is happening is this will keep on toggling until you deactivate the clock or you significantly change one of the input, which will affect the output. Okay, or else it will toggle between 1010 0101. Got it? So that's why we go for a master slave JK flip flop. Okay, now in master slave also there are two types, AOI gates and NAND gate. Which one you want to do? In master slave JK flip flop NAND, because NAND gate will require even more transistors.
Right.
So we'll go for AOI gates. NAND gate is easy to remember, you don't have to do anything, but this is also fine, and NAND gate is also fine. I'll show you both, only this do the design for only one. Okay, let's start. So we will be doing, I told you why it is required to eliminate the race condition. Master slave JK flip flop. Okay, so we will be using AOI gates. So tell me, first is the master, right? AOI gates, this what I mean is the gate level schematic is slightly trickier. I mean, you don't remember where is going where, what is going where. So I will explain it still, no problem. So we'll have to draw individually JK flip flops and then connect them together for master slave. Alright, so these are my individual JK flip flop using AOI logic. Finally, this will be QS, Q slave bar, and this output will be Q master bar, correct? And your input will be clock. It has to be in this manner only, whereas NAND gate it's very simple. This is K, this is J, this will go over here and join to the slave. This will go over here. Please draw the diagram also along with the string. Okay, and then we have a cross coupled cases at the output. Okay, this is one. Second also you draw it. This is clock. This also you draw it like this, same. Yeah. How will you connect the first stage? This is master stage from year to year, and this is slave stage. Alright, how do you connect this? You connect this like this. So this QM will go as one input over here. This QM bar will go one input over here. So this is QM bar and this is QM. Alternate you give. Slightly strange the way in the manner in which they are connected, but that is the way it is. Okay. Okay. Master output is given to the slave input. So master is a positive level triggered. It is activated when the clock is 1, and slave is a negative level triggered. What do you mean by it? Anyone? So if this is clock, master is activated by this positive level triggered. Okay, and slave is activated by negative level trigger like this. Got it? Hello?
Yes,
So positive level triggers when the clock is 1. So when the clock is 1, slave is active. When the clock is 0, when the clock is 1, master is active. When the clock is 0, slave is active. So we'll write it somewhere. Clock 1, master is active, and when the clock is 0, slave is active. Oh, this is clock bar, sorry, this is clock bar. Please do the changes over there. So when the clock is 1, the inputs J and K allow the data to be entered into flip-flops. That is, first stage outputs are set as per J and K inputs. Okay, so QM and QM bar are set as per J and K inputs if the clock is 1. When the clock is 0, slave flip flop is turned on. Okay, and a change occurring in JK input is never reflected directly to the output. Are you understanding what I'm saying? What I'm saying? Okay. No, I'll again say, when the clock is 1, this is 1, J and K inputs are allowed to enter into the master flip flop, right? First stage. So first stage QM and QM bar are set as per J and K inputs. Agree to this?
Right.
Now when the clock becomes 0, that means clock bar becomes 1, the slave flip flop is turned on. Slave stage is turned on, right? Now if a change is occurring in J and K inputs, this J and K inputs, now if any change is there, they are not directly reflected to the outputs.
Right.
So we'll see this. So this will happen when J and K is 1, toggling occurs, but it eliminates the possible of uncontrolled oscillations. We'll see this. Toggling still occurs over here, but it will not lead to any drastic effect. Let's see this. So first of all, we will check its write its equation QM. We write 4 equations now. First is QM, QM bar, QS, QS bar. You understand why the suffix M and S, master and slave. So tell me, what is QM? Hello. QM. This is QS. This is QS bar. Okay. So what will be this? QS K clock. Okay. This will be clock J QS bar. So what, tell me, what is QM? QM will be K dot clock dot QS, right, plus QM bar, right? This is QM bar. Yes or no? The whole bar. Agree to this? You all are there?
Yes.
Okay, okay. This is J clock QS bar plus QM, the whole bar. Similarly, QS will be this will be what? QM bar clock bar, right? This will be QM into clock bar. This will be QS bar. This will be QS. Now tell me, QS is QM bar clock bar into, or plus QS bar, right?
Yes. The whole bar.
The whole bar. And this will be QM dot clock plus QS, the whole bar. Is this correct?
Right, sir.
नहीं, गलती है ना, एक क्लॉक बार होना चाहिए ना यहाँ पे, क्लॉक बार. हाँ, क्लॉक बार. So we need to implement them, these equations, using static CMOS logic. So master stage के लिए will require 2 stages, QM and QM bar, and slave stages also will require 2. Also all of them will be connected together. Sorry?
To draw them separately or together, like.
So
two for master.
QM and QM bar same together, QS and QS bar together.
Okay.
We'll do it now only, na, don't worry. We'll do it now only. Okay?
Yes, sir.
Alright, let us start. So you have written the equations. I was waiting for you all to write the equations.
Yes.
Okay, now let's implement first QM, then QM bar, then QS and QS bar. So here we have 3 NMOS transistors in series with parallel to QM bar. Okay, so be very careful in implementing this. Alright, so let me start over here with NMOS transistors. First write the inputs. K clock QS, that is in parallel with under the NMOS transistor with input as QM bar. This is my NMOS pull down. Now PMOS will be, these three transistors will be in parallel, right? Yes or no?
Yes.
And they will be in series, right? Let me draw it over here a little bit. So inputs are K clock QS, this is VDD, they will be in series with, this is also QM bar. Alright, so this QM and this QM bar are one and the same. Agree? Now I'll draw the what is the output? Output is,
QM.
this is QM. Yeah, that's right. Now similarly on the same lines I will draw QM bar. QM bar, this was QM, right? I will draw QM bar. So over here only I'll draw it. Exactly replica of the same circuit, but transistors orientation and all we have to take care because we have to connect them together there. Now let me draw it. Okay, so here instead of three transistors in parallel over here, orientation I'll change it. Here I'll connect QM, right? Here will be three transistors with the input J clock and QS bar, right? This is my output, and upper one I'll draw them again in parallel. So this will be J, this will be clock, and this will be QS, right? QS bar. This is VDD, and in series we will have, this will be QM. Alright, so this QM and this QM will join together to this QM, and the output of the second stage is QM bar. So this QM bar I'll join together to this QM bar. Got it? If anyone has written something?
So just a minute.
Yes, I'll wait. You have a doubt? Yeah, automatically your attendance will be marked. Anyone has a doubt? Yeah, you can ask your doubt. Okay. Anyways, you can encourage to ask your doubts. This is the last topic, master slave JK flip flop. Then I'm ending the today's session. So just 5-10 minutes more. Did you complete this master flip flop section, master stage?
Yes, sir.
Okay. Now exactly similarly we will draw the slave stage carefully. So here we have QM, here we have complementary signals, don't worry about it, you just write it. So here we will have two transistors in series with the input as QM and clock bar, with a transistor in parallel, this will be QS. So on the pull up side we have two transistors in parallel again, NMOS, PMOS transistors with the input QM bar and clock bar. Alright, and this will be in series with transistor with the input QS bar, and the output will be QS, right? This will be QS. Let me not use this color. This is QS. So similarly, I'll draw it for I've drawn for QS. Now I'll draw it for QS bar. So here we'll have another two transistors. Here it is in series. I hope you are drawing at your end. This is QM, this is clock bar, and this is QS, right? This QS only. Now let me check. Yeah.
Sir, in the first network of slave, in the pull down network, it will be QS bar, right? You have written QS.
Here.
Yeah.
Okay, okay, fine, fine. Agree. This will be QS. This will be QS. This will be QM. Clock bar. Alright. We cannot connect everything, but at least the slave and the master outputs QM and QM bar, QS and QS bar, that we can connect. So this QS can connect it over there, and QS bar, green color, I'll connect it over here. This is QS bar. Yeah, now this is complete. The design is complete. Note down the design. The transistor count is master stage, you require total 16 transistors. Slave stage, you require total 12. And anything else you require? For clock and clock bar, right? You require two more, clock and clock bar. J and K are not complementary, right? हाँ, ये NAND gate नहीं है. NAND gate के लिए you require complementary signal also. So you will require even more transistors to implement if you use NAND gate design. But NAND gate is a universal gate, so they are also preferred. I'll show you the design. That I'll not do. That I'll leave up to you for home assignment. NAND based clocked master slave JK flip flop. That you can do it on your own. Alright? Design completed. So as I told you, it's not so hard. It's only that you require complete concentration. If you get distracted, you will write the wrong thing and you will get, you can reduce the chances of getting high marks. So basically it's a synchronous sequential circuit, this master slave JK flip flop, and it passes the data only during active phase of the clock, right? Can I go ahead?
Yes, sir.
Okay, this is complete. Now I will show you the design for other one. I'll not, if I do it again, it will take 10-15 minutes. JK flip flop, NAND base. Let me check over here. हाँ, ये देखो. Up till here we have completed, right? This is NAND based JK flip flop. See, the design is different. Here it is QM is directly going over here, QM bar is directly going over here. Here the third input is going way up till QS, and this is going till QS bar. That's the difference. So master slave using JK flip flop using NAND base is simple, but then the transistor count will increase. Okay. So here also we'll calculate QM, QM bar, QS, QS bar. This I'm not doing it. I'm just revising it for you. Will you do it on your own? The design? Yes or no? Hello?
Yes, sir.
Okay. This is the truth table. The expressions QM bar, I have taught you all how to do it. QS and QS bar. And this is the design. As you can see, we were getting how many? Here 16 plus 12 plus 2. So total कितना हो गया? 20, 30. Here you see how many are required? 16 plus 12 plus 6. 34. As I told you, number of transistor count will increase. Just because कॉम्प्लीमेंट्री सिग्नल चाहिए ना जे एंड के लिए, दैट्स इट. So design is similar, but only thing is this transistor count will increase. All right. Okay, students.
Yes, sir.
Now I have to explain you this one, and then we'll go. There is a race around condition. Yeah, there's that problem. This problem of one's catching. See, when the clock is high, um, there is a glitch in one of the inputs. For instance, there is a glitch in J and K line. May set or reset the master latch. Thus causes an unwanted state transition, which will then be propagated into slave stage during the following phase. This problem can be eliminated by large extent by building edge triggered master slave flip flop. अभी जो हम लोग ने सीखा है, what is this? Hello, this is level triggered ना?
Yes, sir.
Let me. हाँ, edge triggered you can build it using this is level triggered. What we have studied. This is, yeah. Now this example, how will I explain? Let me consider this gate. Wait, huh? Yeah, let me keep it over here and let me explain this quickly because this is important. I can use this, right? Okay. Now let's see this first case. Clock is 0. Hello, listening?
Yes, sir.
Clock is 0. Let's say the previous state is J and K is 0 0. So what should be the output? Previous state, right? Let's say the previous state right now is 0 1, and slave state will also be 0 1. So far so good.
Yes, sir.
Okay. Now clock has become 1. J and K is 0 0. So what it should do? It should hold the state, right?
Yes.
So this will be 0 1 and 0 1. Second also clear? Okay. Now third stage. Clock is 1, J is 1, K is 0. So what should happen? It should set the output. So QM should become 1, right? And QM bar should become 0, right?
Right.
And now, so here I'll come again here. So QM will become 1, QM bar will become 0. So what will happen now? And clock is still 1. So slave stage is inactive, right? So it won't affect the slave output directly. That is what I meant. तो toggle हो रहा था ना, नहीं होगा वो. Are you understanding?
Right.
हाँ, I mean toggle will happen when both J and K are 1. Let's see that stage. So QS and QS bar will be 0 and 1. Why 0 and 1? Because they are holding the previous state. ना off है ना वो.
Right.
Now clock became 0. Okay, clock became 0 means irrespective of J and K, master का output change नहीं होगा. देखो 1 and 0 ही है. But slave का output will change, right?
Yes.
Why it will change? Because now slave output is receiving, this is 0 and this is 1. So उसके लिए ये J and K है ना. I mean, okay, so QM will become this QS will become 1 and 0 because J is 1, K is 0. So this is getting reflected. This is clear? 1 0. Because J is 1 now, na? J is 1, it will affect QS now because QS is active. So QM is not affecting QS. Understanding?
Yes.
Now clock is again 0, J and K is 0 0, it will hold the previous state, so it is correct. Then again clock is 0, J is 0, K is 0. So master ka state is not changing, it is becoming 1 0 only. But slave is becoming also 1 0. Why? Why this is happening?
Because it will hold the previous
Which previous state? Master? A slave?
slave.
See, slave state will not change until master is active again. एक बार सेट हो गया तो वो सेट ही होगा, रीसेट हो गया तो रीसेट ही होगा until clock becomes 1 again. बराबर?
हाँ sir.
हाँ. So slave output depends upon the master. Master active होगा, it will change the input, then only it will reflect in the slave. Now let's go over here quickly, please. Now we are in this stage. Let me change the color. Now clock is 1 again, and now J is 0, K is 1. So what should be the output? Reset हो गया ना, ये 0 1 हो गया, right? Correct ना? But what will be the slave output? Slave output will remain 1 and 0. Why? Because clock 1 में slave off हो गया. Slave is off. That's why output will remain as it is, 1 0. Correct?
Yes, sir.
Now again clock is 0. J and K state are not changing. So QM master output will remain same. But what about the slave output? Because अभी active हो गया ना. Clock is active. So it will take the inputs. And what are the inputs? 0 1. So 0 1 के लिए वो क्या देगा? 0 1. Got it? It will reset ना. Reset means 0 1 हो गया ना.
So, sir, whenever a particular state is off, at that time it will hold that value previously.
नहीं. When the slave will hold the value when it is off.
Yes, sir. Like if we give, let's say, clock 0, so
हाँ.
the clock bar will be 1, so the master will be off, but the slave state will be on.
Yes.
So in that case, irrespective of your JK inputs, the output of slave will change.
हाँ. Yes. When clock becomes from 1 to 0.
Right? Yes, sir.
Okay.
So, in that case, sir, your JK output will remain same. The master output will remain same, but slave output will change from.
Yes.
because of the-
Only when the clock changes from 1 to 0.
Yes, sir. Understood.
Now again see here, see again the clock is 0, J and K is 0 0, so it should hold the previous state, right? So it is holding the previous state, no problem. Now the clock has become 1, so master active हो गया, J and K is 0 0, it's holding the previous state, and master is following that, right?
Yes,
Sorry, slave is following the master.
slave is following.
हाँ, slave is following the master. अभी ये प्रॉब्लम आ गया, इधर एक ग्लिच आ गया, लेट्स से, राइट? ये स्टेट देखो अभी, clock is 1, J is, let's say for some other reason J 1 हो गया and K 0 हो गया for some reason. Now what will happen? What should happen? This should be 1 na. J is 1, K is 0 means it should be 1 0, right?
Yes, sir.
So master का output changes from 1 to 0, from 0 1 to 1 0, and the slave will remain same because it's off na.
Yes, sir.
हाँ. Now again one clock is 1 and your JK is 0 0, so it will hold the state 1 0, but
Yes.
slave to on नहीं हुआ, तो it will also be 1 0 1 now. Now the clock has become 0, so what will happen? Slave will be active, master will be off. So J and K is 0 0, it will hold the state 1 0, right?
Yes.
Now tell me ये 1 0 क्यों हुआ? Because when the slave is on, when the slave is working, it will follow the master output, right? और master output क्या होना चाहिए?
1 0.
हाँ, 1 0. So it is following 1 0. So is this a problem?
Yes, sir.
Not a problem. Don't see any problem over here. अच्छा चलो 1 1 में आते हैं, 1 1 में प्रॉब्लम पता चलेगा. Okay, let's move ahead. Okay, so now next case में again clock is 0, J is 0, K change हो गया, मतलब this has changed, K should be 1. Okay, so when the K is 1, master is off, slave is on. So master is off means it will hold the state 1 0, but slave will also follow the master 1 0, correct? Yes or no?
Right.
Now clock is 0, J and K 1 1. ये देखो ये condition आ गया अभी. J and K is 1 1. What should happen? QM and QM bar should be, मतलब ये that not allowed state is gone. It will hold the previous state because master is off here. So it will hold to 1 0 and slave will follow it, right? तो 1 के लिए रेस अराउंड आई मीन 1 0 आ रहा है. नाउ देखो अगर रेस अराउंड होता है क्या नहीं यहाँ पे. नेक्स्ट, नाउ नेक्स्ट केस में क्लॉक हैज़ बिकम अगेन, नाउ लेट मी यूज़ येलो कलर अगेन 1. अभी देखो 1 हो गया एंड जे एन के इनपुट इज़ 1 1. तो क्या होगा अभी आगे नेक्स्ट 1 1 एक्टिव हो गया ना अभी. तो 1 1 के लिए क्या होना चाहिए, इट विल टॉगल ना. सो पहले 1 0 था, इट विल बिकम 0 1. बट स्लेव कैन नॉट फॉलो बिकॉज स्लेव ऑफ है ना, तो इट विल होल्ड द प्रीवियस स्टेट. समझ गया.
Okay.
हाँ, नाउ व्हेन अगेन द क्लॉक इज 1, जे इज 1, के इज 0, इट शुड बी सेट ना, सेट बराबर है.
Set.
हाँ, तो ये रॉन्ग हो रहा है यहाँ पे, ये रॉन्ग हो रहा है यहाँ पे, दिस इज रॉन्ग. यहाँ पे प्रॉब्लम हो रहा है देखो.
Sir.
क्लॉक इज, व्हाई इट इज नॉट हैपनिंग.
Sir, because this master is on and slave is off, so it is following it.
मास्टर इज ऑन.
Yes, sir, master is on.
हाँ, एंड स्लेव इज ऑफ. सो जे के लिए, जे मतलब इट शुड बी 1 ना, आउटपुट क्यू एम शुड बी 1 बट इज 0.
Right.
सो ये 1 1 में प्रॉब्लम अभी भी हो रहा है. एंड दिस प्रॉब्लम विल बी रिमूव्ड व्हेन वी यूज एच ट्रिगर्ड जेके फ्लिप फ्लॉप. व्हाट डू यू मीन बाय एच ट्रिगर्ड. ये लेवल ट्रिगर्ड है, मतलब ये पॉजिटिव या नेगेटिव लेवल में होते हैं. इफ एच ट्रिगर्ड मीन्स दिस, इधर दिस इज एच ट्रिगर्ड, राइट. if we have this kind of stuff, then this problem will not happen. You won't get a incorrect output for 1 1. Got it.
Right, sir.
Okay, so that is some problem remaining in edge triggered master slave JK flip flop, which you can remove in level triggered, which you can easily remove in the edge triggered JK flip flop. Okay, if you just make the clock instead of level triggered, edge triggered. So that's why we can call it as a flip flop if it is edge triggered. Okay. So yeah, so that's it for today. These are your waveforms for your master slave flip flop circuit. As you can see, once catching the clock is one glitch. Yeah, यहाँ से चालू होता है problem. Okay, ठीक है. Let it be. I hope you can understand it. So yeah, that's it for today. I'll show you what is pending now. Pending is this topics. D latch, right? Delay latch. So delay latch we will use using static CMOS logic. This will do it next time. It's very easy, straightforward. Then we're using clocked delay latch. Then we'll again do clock delay latch using NOR based design. Then we'll do positive level trigger D latch using CMOS transmission gate and pass transistor logic. Okay, so we'll do these designs. It will take one lecture to complete. Then we'll do dynamic positive edge triggered. Okay, we will also use this negative edge triggered master slave D flip flop. Master slave D flip flop भी है. And then we also have dynamic D flip flop using pass transistor logic, using transmission gate. D flip flop remaining, but lot of varieties are left. Dynamic positive edge triggered D flip flop. Okay, then this is the same. And then we have D flip flop using C square MOS logic. And finally positive edge trigger D flip flop using C square MOS logic. So these all topics are remaining still. So we will cover it in the next class, in the actual classroom. Okay, so that's all for today. If you have any queries